The first talk is going to be given by Ignacio Cascudo. This is a joint work with Bernardo David about publicly verifiable secret sharing over class groups and application to DKG and Yoso.
Yeah, thanks. This is, as you can see, a paper on publicly verifiable secret sharing. So let me first explain what this concept is about. So a PVSS scheme is a secret sharing scheme that provides additional proofs of two things, and these proofs are publicly verifiable. So basically the proofs that we want are sharing correctness, meaning that the dealer proves that the shares that she's sending are correct according to the underlying secret sharing scheme. So for example, for Samir secret sharing, what the dealer is proving is that the shares are evaluations of a polynomial of degree at most t in the public points that define the scheme. For reconstruction, what we require is that the parties prove that the shares that they are pulling together, they are really the shares that they received from the dealer. Now, because these proofs need to be publicly verifiable, clearly we need something that allows a public verifier to check these proofs. So we cannot have all the communication be private between the dealer and the share receivers. So what we do is to have a public balloting board, and the shares are going to be delivered through public key encryption over this balloting board. So basically there are going to be public keys for each of the parties that have their corresponding secret keys, and the dealer takes the secret, constructs the shares, encrypts the shares, and posts those encryptions in the balloting board. So then now we have information enough to have a non-interactive zero-knowledge proof of correctness, because the prover can show that there exists a polynomial of degree at most t, such that the evaluations of this polynomial are the plain text of the ciphertext that are in the balloting board. Same for reconstruction of the secret. I mean, the parties can prove that the shares that they are posting for doing the reconstruction, they are the ones that correspond to the ciphertext that the dealer posted before. There are PVSs based on different assumptions. There are some constructed from the Pallier encryption, also from lattices, but I'm going to focus on the discrete logarithm based. And again, there are many constructions of this type, but well, let me highlight one which is very well known from Schumacher's 99, and then three that Bernardo, my co-author, and I have had in the last years. The last one is with Lydia Garms and Anna Skongring. And all these constructions have these features in common. So basically, we are working on a cyclic group of prime order with a hard discrete log, also usually hard DDH too. And what the parties get after the decryption, it's actually not the field shares, not the Shamir shares, but what they are getting is a generator of the group raised to these shares. So the secret that they can reconstruct by interpolation in the exponent, is actually G to the field secret. Now, this still has applications, has many applications, like for example, one could still do MPC for linear functions whenever the output is small, like for example in the case of elections, because parties can aggregate shares linearly by operating on the group, and because the output is small, they can, in that case, break the discrete log if they know that the result is in a small range. You can also use this for randomness beacons, as we did in Scrape and Albatross. And you can even turn this into a PVSS of a field element by essentially secret sharing a key, a random key, and then like broadcasting the one-time path of your secret with some random oracle applied to this key. But then you lose all kinds of linearity properties because you are using this random oracle. So in particular, what this is not so good for is for distributed key generation. Now, here I'm talking about distributed key generation for discrete log-based schemes. I will explain this further in the next slide. But also, like, it's not good for MPC in more general settings. So, when I talk about this distributed key generation, I mean, how would learning sigma I instead of G to the sigma I help? I can explain, first of all, what is the goal for this distributed key generation. We would like that parties establish common threshold public key of the form G raised to a threshold secret key. And then this threshold secret key should be shared among the parties. So parties should know Shamir shares of this key. So if we have a PVSS that allows to recover Shamir shares of a secret, then one strategy to implement this DKG is to have every party construct some random element or choose some random element, then share it with the PVSS. Then parties determine the set of correctly shared secrets. And here I'm, by the way, talking about the synchronous model. Everyone is going to reconstruct the same set because the proofs are publicly verifiable. So everyone has the same information to verify the proofs. So everyone can agree on the same set without interaction. And now parties can aggregate the shares that they received in the correctly shared secrets, publish the value G raised to that share, and then reconstruct via Shamir interpolation or Lagrange interpolation the threshold public key. Of course, the parties need to prove that the shares that they are giving are correct. But this is also possible in PVSS, as I mentioned before. So the contributions of this paper are that we are going to construct a PVSS that allows to recover these field shares. And we are going to do that using class groups. Now, one thing I didn't say here is that PVSS works, is secure against any honest majority. So 2e is smaller than n-halves. And we achieve some very strong notion of privacy called int2, which is indistinguishability of secrets that may be chosen by the adversary. And the sharing requires to broadcast only n+1 class group elements. And our proof of correct sharing is constant size, just 3 integers of group size. From there, we can construct distributed key generation protocols. We can construct a 2-round protocol with that allows to get an unbiasable public key. And this is round optimal. This is proved by Katz in an upcoming work in Crypto 24. And we get a gain of around 5 to 7 times what can be obtained from Palier, which is the construction that is suggested in Katz. Also, we could construct a 1-round distributed key generation protocol, but in that case, we have to allow that the adversary may bias the public key. But there is another paper that has done this a bit better than us, so I will mention it later. We also give another application, which is to MPC in the YOSO model, where we can have MPC with a transparent setup based on class groups. But I'm not going to talk too much about that here. Now, let me give a bit more details about how we construct this secret sharing scheme. So We are using this Castaños-Leguilemy framework. This is a framework which is, again, based on class groups, on ideal class groups of number field, quadratic number fields of imaginary, of negative discriminant. So in that case, we have the possibility to construct cyclic subgroups of the class group that in turn can be factored into two components. One is a class group. One is a group of unknown order, and the other is a group of order that we can choose, and that has an easy discrete log, even if the order is very large. And then this allows us to define an El-Gamal-like encryption under certain assumptions that I'm not going to get into, but that allows to encrypt messages that are modulo Q in the exponent of this subgroup of order Q. And so when the decryptor recovers, as in El-Gamal, exactly as in El-Gamal, this value, F to the M, because the discrete log is easy, it can recover also M. So this is what allows us now to turn a PVSS that we had in Eurocrypt 22 into, or have a version of this PVSS that allows us to get the field shares. Because in the scheme that we had in Eurocrypt, one thing that we did in this work is to reinterpret that as some kind of El-Gamal multi-encryption. This means that sharing, what happens in the sharing is basically that you are constructing, you are encrypting the shares with El-Gamal, but with a common first message, which doesn't depend on the message that you are encrypting. Now, here we can do the same by replacing El-Gamal by this Castaños-Leguilemy encryption scheme. And now we can retrieve this share sigma I, as I explained before. Now, of course, things are not so easy, and we need to change our proof of sharing because there are certain things that in the previous construction that here don't work exactly like that. To mention this, a little bit about this. So in this paper in Eurocrypt 22, what we were using was something called a scrape trick that we had in some work before, which is a very simple probabilistic test that something is or some vector is a Shamir sharing. The idea is simply to see that the set of Shamir sharings as a Reed-Solomon code. You sample a word from the dual code, and then you check that the inner product is 0. Now this is a probabilistic check that something is a correct Shamir sharing. And because it is linear, we can do all kinds of tricks with this. We can use it in the exponent to, in the particular case of Eurocrypt 22, reduce the proof to some discrete log equality proof by just sort of canceling out the sort of shares in the exponent. And that's what we do in this Eurocrypt 22. It's a bit technical, so, but more or less that's the idea. Now, in our work, that doesn't quite work like that, because the problem is that even though the group generated by F is of order Q, not all the groups involved are of order Q. So that means that it's a bit subtle, but the adversary can cheat in this proof by multiplying the shares or the purported shares by some elements. So in order to ensure that the dealer is doing the correct thing, we have to add some random small multiples of Q to these WIs that were sampled from say, set Q or from the range 0Q. So this is one thing. You can see it in the paper. The other thing that is a bit problematic here is the discrete log equality proofs, because proofs of knowledge of discrete log are quite expensive in class groups. But what we show in this work is that we can actually replace almost all the proofs by sound proofs. So we only need proofs of knowledge when the parties are like proving knowledge of, when parties are posting the public keys. And then proving knowledge of the corresponding secret key. In the rest of the proofs of the construction, we are okay with sound proofs, and then we can use a more efficient construction of proofs that was given by Brown et al. In Crypto 23. So this is nice. Now I have to mention that there is another work that we got aware of a little before a submitting. This work has been accepted in CCS 24 that presented a publicly verifiable secret sharing that has exactly the same sharing encryption as we do. But they have a different correctness proof. And in that work, they were more focused on the one-round distributed key generation as a goal. Now, the comparison between these two works, you can see their paper for a detailed comparison, but the summary is that our PVSS is more communication efficient, has also a stronger notion of security based on indistinguishability of secrets, while they leak some information about the secret, because that's okay for their application. Now, when it comes to the one-round distributed key generation, their scheme is more efficient because, in few words, they are able to reuse some of the communication that they had for the proof of sharing. Yeah, so you can check the details in their paper if you're interested in. One thing that I should mention is that they say that we are based on a non-falsifiable assumption, which is this thing that was used in Brown et al. It's an assumption on class groups called the rough order assumption. But I should mention that this is not strictly necessary in our work. We could replace our proofs of our sound proofs of discrete log equality by other proofs that are not proofs of knowledge and that don't require that assumption. So, yeah. Now we have an implementation. This is by Rasmus Frey Sørensen. And it's quite fast, and we can see that actually the main bottleneck right now seems to be the verification of the share openings that I haven't really talked too much about. It's just, again, a discrete log equality, but now you have to verify all the openings of the parties that are reconstructing the secret. One thing that I should mention about this is that this is for the case T smaller than n halves. If we have like a supermajority, if we have like 1/3 of the parties being corrupted only, one wouldn't need to do these opening proofs, because actually one could use error correcting to actually reconstruct the secret even in the presence of wrong shares. So this is only for the case where T is larger than n/3 that we need to do these share opening proofs. So it's a bottleneck, but it is not so bad. And yeah, as conclusions, basically this is a bit repeating what I have just said, but we have presented the PVSS over class groups. That is based on our previous construction in Eurocrypt 22, but allows to recover field shares. We constructed 2-round and 1-round distributed key generation protocols from this. And we have also construction of MPC in the YOSO model. The implementation is quite fast, but the implementation is not in the paper, by the way. We have done it afterwards. The main bottleneck is the verification of all these discrete log equality proofs, which is not strictly necessary in the case where we have more honest parties. Yeah, thank you.
All right, so we have time for one very quick question.
I will try to make it short. Thank you. Thanks for the nice presentation. So just a short question. You mentioned this recent related work doesn't basically provide full security because they reveal G power S. Does it mean that it's not secure against rushing adversary that you can,
well, the thing is that no, what I mean is basically we have our definition of security in terms of indistinguishability of secrets. But if you are leaking G to the S, then you cannot have this security because basically the adversary could just construct S0 as 1, then give it to the dealer. The dealer send you the sharing of that, and then you can see which secret was shared. But this is for the DKG construction. This doesn't matter because you are going to have to leak that anyway, because you are going to construct the public key. Yeah.
Okay.
I hope it's. Otherwise, we can talk about it later.
Okay. No. Okay.
Okay, we need to shift. So thanks again for the talk, and let's move to the next one. Yeah, thanks.
Thank you.
All right, so the second talk of this session is joint work by Eman Tamaji, Hai Nguyen, Anat Paskin-Cherniavsky, and Xiuyu Ye. It's about constructing leakage-resilient Shamir secret sharing over composite order fields, and Hai is going to be giving the talk.
Thank you for the introductions. I'm going to talk about constructing leakage-resilient Shamir secret sharing over composite order fields. And this year, I work with Hai Tamaji, Anat Paskin-Cherniavsky, and Xiuyu Ye. So threshold secret sharing is an important building block in many cryptographic protocols. And it splits a secret S into shares, so that any greater than or equal to k shares can reconstruct the secret. And the security guarantees that any less than k share reveals no information about secret. And so that this is a all or nothing construction model. What I mean is that the adversary can get full information of some secret and no information at all about other secret. However, such all or nothing corruption model is not true when considering structural attacks. So when we consider structural attacks, adversary can get partial information from every secret share. So to capture that concerns, in Crypto 2018, Ben Hamodan, Legagwa, Ishai, and Rabin formally introduced the local leakage model. And in this model, the adversary can get independent leakage from every share. Now, the scheme is secure on leakage resilience if the adversary views is essentially uncorrelated with the secret. Okay. So given that in mind, it is natural to ask that how to securely instantiate Shamir scheme against leakage attacks. So you can ask, why Shamir? Because it's everywhere. And what leakage we are considering? So in this work, we consider probing attacks. And here is the current state of the art. In Eurocrypt 2021, Maji, Nguyen, Paskin-Cherniavsky, Rad, and Huang proved that Shamir secretion scheme over prime fields with random evaluation places is secure. So it is natural to ask, how about composite order field? So answering these questions is the focus of our work. Okay. So before stating our results, let me briefly recall Shamir scheme and the leakage model. And here is a summary scheme. Probably most of you are familiar with. It is a polynomial-based construction. And to share a secret S, it picks a random polynomial of degree less than the reconstruction threshold. such that the secrets equal to the evaluations at 0. And shares are evaluations at distinct places. Okay. And our work considers Shamir scheme with random evaluation places. So it means x1, x2, and xn are sampled randomly. Okay. And here's the leakage model. We consider physical bit propping, introduced by Ishai, Shahai, and Wagner. So in this model, every field element is stored in memory at D blocks, and each block stores one FP element, and that FP element is stored in binary representations with log2 of P bits. So in the propping model, ZVC gets, say, m bit physical bit from every share. Okay. And for example, for single block leakage, the adversary gets information about one block of every share. As you can see in the picture, the adversary can get the second rightmost block from the second share, from the share S1, okay. And so on for S2 and Fn. Okay. So here is here's our first result. So we show that random evaluation place just secures Shamir scheme. And in more detail, we show that if the total leakage, that is Mn, less than rho times k minus 1 lambda, then the scheme is secure. So note that k minus 1 times lambda is roughly the entropy of the shares. So our results saying that if the total leakage is a scaling factor of the total entropy, then it is secure. And our results hold for any reconstruction threshold that is greater than or equal to 2. And also, it holds for any large characteristic 2 fields. And this is widely used in many protocols. So our results imply that we can construct liquid resilient secure computations using GMW-style protocol. Okay. And compare with the results of a prime field, then the permissible leakage is slightly smaller. So we have a factor of rho, and it depends on the characteristic. So in the technical part, I will give you some intuitions why this is the case. Okay. So the randomized construction is good, and it achieves good parameters. However, in some setting, when the adversary can set the randomness, then it becomes insecure. So one natural question is to de-randomize the construction. So that is our second result. So we consider single block leakage, as you see in a few previous slides. And we show that there is a dichotomy. Shamir scheme is either perfectly secure or completely insecure. And there is no partial insecurity. So when it is insecure, we can also construct an attack that had distinguished advantage 1. And we also have an algorithm to classify which one is secure, which one is not secure. Okay. So the algorithm takes as input evaluation places, and it outputs whether it is secure or not. And the algorithm is very simple. It computes a set of G factors S. I'm not going to describe exactly what is the set S, and it is upside D. And then we check that if there exists a set n elements in this set, so that when we shift the evaluation places by these factors, it results in a set of vectors that are linearly dependent, then the scheme is insecure. And if they are all linearly independent, then it is secure. Okay. So let me put our first result in more broader context, when we consider different leakage models. And as you can see in the table here, all the previous work consider Chamier scheme over prime field. And they consider different leakage model, the local leakage model of physical bits, and a more general bounded joy leakage. So our work consider composite order field. And this is the first one proves that over composite order field, Chamier scheme is leakage resilience. Okay. And another observation is that for physical bit leakage model, we can get very good parameter. So reconstruction threshold can be very small. It doesn't need to be greater than or equal to 2. But for the other, the reconstruction threshold need to be quite large. It has to be at least half of n. So for the rest of the talk, and here are some other related works. And the problem is, the leakage resilience problem is closely related to repairing error coding codes. This is an interesting problem in information theory. And also there are 2 lines of work in leakage resilience scheme. One is construct a new scheme that achieves very high leakage resilience. And another line of work is to put existing scheme, like additive scheme and Chamier scheme, leakage resilience. And our work belongs to the second line. Okay, so for the rest of the talk, I will give an overview of our randomized constructions. If you are interested in the second result, the randomizations, you can take a look at our paper, or we can discuss it outline. And at high level, to prove the results, we extend the analysis of the result over prime field, and we use Fourier analysis and probability techniques. Okay. So there will be 2 main steps here. In step 1, we show that the distinguishing advantage is small on average. And then, using this bound, we apply standard probabilistic techniques to show that it is secure for most evaluation places. Okay. And let me highlight the key technical ideas in our paper and how it different from the proof over prime field. So the key thing here is to bound the number of solutions of a system of equations. So we fix an vector alpha. It is in f star p to d to the k. So there is a typo there. And we consider a system of equations. For intuition, the thing about k equal to 3. And vector alpha is vector 1. And we are interested in counting how many solutions x satisfy that also x1, x2, x3 are distinct. So to bound this, we employ a contemporary Bezout-Lie theorem over composite order field. And actually, this is proved very recently in 2021. And for the prime field, Magier et al. Used the result by Gouli in 1996. And as I mentioned before, there is some subtleties, and I will explain it more details in the example. Okay. And if we just naively apply some analysis over prime field, it does not work. Okay. So here is a Bezout-Lie theorem. Let me first give some intuition about Bezout theorem before talking about Bezout-Lie theorem. So if we have a system of equations over, say, kn variables and k polynomials, and the classical results show that the number of zeros of this system is bounded by the product of the degrees. However, over finite fields, the problem becomes more complicated. And in this case, actually, a similar result hold, But now you can see in the theorem, it's saying that the number of isolated zeros. It's not the number of zeros of a system. Okay. So what is isolated zeros? So a vector A is an isolated zeros if it is a root of zeros of the system of equations, but it's not a zero of the Jacobian determinants. Right? And the Jacobian determinants are defined in that way. It's not important to understand exactly what is that determinants. Okay. Okay. And here is the examples. First, let me give a quick overview how the proof in MNPS 21 works. Consider a very simple example, and we compute the Jacobian determinants, and it equals to 6 times the differences between pairwise of the variables. And you can observe that the Jacobians is not equal to 0 if and only if all the xi's are distinct. So in this case, it means that the number of solution x in which they are distinct is exactly equal to the number of isolated zeros. So we can just apply the Bézout-Lie theorem to get the bound. So what happens for our composites of the field? And in this case, it is more involved. And actually, we observe that when P is big, then the same analysis, the same idea works. Actually, the typo here, P should be strictly greater than 3, then the same analysis work. Okay. However, when P is small, for example, P equal to 2 or 3, it doesn't work. And why it doesn't work? Because now you observe that the Jacobian determinants is equal to 0 for every vector A. Over finite field with characteristic 2, the Jacobians, it have a factor of 6 there, so it's equal to 0 for every A. So the same idea doesn't work. So how do we overcome this problem? So by that observations, because of the factor of 2 of the quadratic equations, when we compute the Jacobian determinants, it makes the determinants become 0. So our idea is to remove all the equations with even power. Okay. And then we end up with a system of equations with two polynomials. Okay. But there are actually 3 variables, so we fix one of them to get a square system so that we can apply the Bézout-Lie theorem. And now if we compute the Jacobian matrix, the determinants equal to 3 times x1 minus x2 square. And observe that now when x1 and x2 are distinct, the Jacobian determinants is non-zero. So exactly same as before, after removing the equations. And because of removing all the equations with even power, it's caused a loss factor. That's why we get 1 minus 1 by p. And now, what if the characteristic equal to 3? So the determinants equal to 0 when x1 equal to x2, or the sum of the 2 variables equal to 0. And for the last equations, x1 plus x2 equal to 0, this is a new and unexpected way making the Jacobians 0. So it's not exactly the same analysis there. So in general, the Jacobian matrix is a generalized van der Waals matrix. Okay. And identifying the zeros is an open research problem in mathematics. And how our work overcome this? We do not identify exactly all the zeros. We just want to have an upper bound on this. And we managed to prove an upper bound for this. And that suffices for our proof. And in the proof, we also bound the L1 Fourier norm of the liquid functions. And consider a very concrete problem. suppose the leakage function is a least significant bit, and the observed leakage is 0. So the Willis set is a set S identified there. So the LSP of the first block, x0, equal to 0. And we are interested in bounding the L1 Fourier norms of these functions. Actually, it's the indicator functions. Okay. And here's a key observation, is that the L1 Fourier norm preserves from the intention fields, or the composite order field, to the base field, Fp, where here's T is a set of all the even number. So it means we're looking at the observed leakage restricted to only the first block, x0. And then we reduce the problem to the problem over the prime field, and we just apply the results from that paper, and we get the bound. So to conclude, we have the two main results. The first one, we show that random evaluation places yields a CQ scheme. And we also have an algorithm to classify CQ evaluation places. And that is, thank you. And I'm happy to take any questions.
All right. If there is a question, we are slightly short on time, so if there is no question, I suggest we move to the next talk directly. Oh, no, okay. Yeah, so let's thank, okay, yeah, a short one, I guess.
Thanks for the great talks. That I want to ask for the security definition that you describe as they are not linear dependent, but lack of intuition why it is the case that it is secured only, it is sufficient to make them non-linear independent, linear dependent.
Okay, that is a good question. So for that one, we consider the reconstruction threshold equal to 2. So think about all the polynomials are linear polynomial, right?
So it's only for the characteristic equals 2 case, though, right?
No, I mean only when the reconstruction threshold equal to 2.
Okay,
and
I
it's
see.
open for k greater than equal to k strictly greater than 2.
I see.
And we consider that if we a lifting theorem, saying that if it is true for true, then it should also hold for a bigger value. We consider that, but currently we don't know how to prove it.
See, thank you.
Yeah.
All right, thanks. So let's thank the speaker again. So let's move to the last talk of the session. So the last talk is about succinct homomorphic secret sharing. This is a joint work with by Damiano, Abraham, Lance Roy, and Peter Scholl. And Lance is going to give the talk.
Right. In this talk, I'll be discussing a technique which we call succinct homomorphic secret sharing and its application to sublinear multi-party computation. This is joint work with Damiano Abraham, Peter Scholl. And thanks especially to Damiano for creating these beautifully hand-drawn slides. A natural functionality in two-party computation is a vector-oblivious linear evaluation. Here we're looking at half-chosen vector OLE, where Alice has a vector x, Bob has a scalar y, and they would like to compute secret shares of the vector scalar product x times y. Vector OLE has been applied to many problems, including oblivious transfer, private set intersection, and zero knowledge proofs. Half-chosen vector OLE is a variation that does not allow Alice full choice over her side of the correlation. That is, Alice doesn't get to choose her share z0, but she does get to choose her input x. In many applications, x is some important secret value that is needs to be chosen, whereas z0 is just a random mask to make sure that Bob does not learn anything. So now that the functionality is clear, I'd like to put a question to you. How much communication is necessary for half-chosen vector OLE? Straightforward approaches would require as much communication as the input size, but this is not necessary. We constructed half-chosen vector OLE protocols with optimal round complexity and sublinear communication complexity. That is, Alice and Bob just exchange a single message each without waiting for each other. So the protocol only needs one simultaneous round after some input independent setup. And they have communication proportional to n to the sum power alpha less than 1. Because of this sublinear communication complexity, we call these schemes succinct half-chosen vector OLE. Here's a summary of our constructions of succinct half-chosen vector OLE. Our first constructions achieve alpha equals 2/3 from a variety of assumptions. Decisional composite residuosity over pi-A groups, decisional Diffie-Hellman over class groups, and quadratic residuosity over RSI moduli each imply similar group-based protocols for half-chosen vector OLE. They differ mainly in the ring they output in. Pi-A produces outputs modulo RSA modulus, class groups output modulo prime, and QR outputs just a single bit. Additionally, class groups do not require some party to have generated an RMS modulus in advance, and so they allow for a common reference string instantiation of the setup, or a condom random string, I mean. For succinct HSS, we need outputs in a large ring, so we'll focus on the DDH and DCR constructions, but not QR. We also showed how to build this from LWE. And we found several stronger assumptions that let us reduce this communication complexity to get alpha of 1/2 rather than 2/3. Inspired by the range trapdoor functions of Garg et al., we showed that power DDH over either pi-A or class groups implies a square root size half-chosen vector OLE. We also proposed a new assumption, power ring LWE, that adapts this kind of square root communication protocol to the lattice setting. So we have several applications for half-chosen vector OLE. First, by combining it with existing constructions of homomorphic secret sharing for RMS programs, we get a primitive that we call succinct HSS. In homomorphic secret sharing, the parties start out with ciphertext encrypting some input X and secret shares of a secret key, and they can non-interactively compute secret shares of some function of the input C of X. Succinct HSS allows some of the inputs to the homomorphic secret sharing to be compressed to some linear size, assuming that the function being evaluated is linear in these inputs. More precisely, if C is a circuit in C1 that outputs a vector, then we can compute the inner product. We can compute the inner product C of X with Y, while only sending data proportional to the length of X and sublinear in the length of Y. We then use succinct HSS to build a pseudorandom correlation generator for n-party distributed point functions, or DPFs. Of cost sublinear in both the DPF size and the number of DPFs to generate. We then used the PCG for DPFs to build sublinear communication MPC for polynomially many parties when evaluating layered circuits by instantiating a sublinear MPC protocol of Couteau. His protocol requires correlated randomness among the parties in the form of shifted and masked truth tables, which is exactly what our PCG for DPFs provides. These truth tables only need to have polynomial size, or must have only polynomial size, which is why we can only save a log-log factor. So we also have a different technique for constructing it, which can save a log factor, but only for sufficiently wide circuits. So how do we build succinct half-chosen vector OLE? Our starting point is a type of protocol, which we call bilinear homomorphic secret sharing. In bilinear homomorphic secret sharing, the parties have vectors X and Y, and they want to get additive secret shares of the inner product of their vectors. We call these two parties the hasher and the encryptor according to the roles in the protocol. The hasher hashes her vector X to get a digest D and sends D to the encryptor. The encryptor simultaneously generates a linear size ciphertext C, encrypting his input Y, and sends these ciphertexts to the hasher. The hash digest D is just a small message. It's independent of the input size. However, the ciphertext has size linear in the input size, n. The two parties can then locally evaluate secret shares of the dot product X of Y. This works similarly to the trapdoor hash functions of Dotling et al. though their primitive is adapted to outputting bits to the encryptor instead of generating secret shares over a larger ring. It may seem hard to use this protocol to build something succinct, as the encryptor is sending a linear-sized message, and the output is only a single field element, which is much smaller than the communication cost of this. However, this protocol has two crucial features for succinctness. One is that the hasher's digest is small, independent of the input size. And the second is that the protocol has only one simultaneous round of communication. Simultaneous communication means that each message from the hasher to the encryptor can be used with against many different encryptor messages, and vice versa. The same encryptor message can be reused for many different hasher digests. In more detail, this is how message reuse gives the succinct half-chosen vector OLE. Let T be the cube root of n, and split up Alice's input into x into t squared vectors, each of length t. These can be arranged into a t squared by t matrix, mx. Meanwhile, Bob prepares his input matrix, my, to multiply mx with. To scale every element by mx of mx by the same amount y, Bob sets my to be y times the identity matrix. Each row of Alice's input mx is then input into a separate instance of the hasher side of the bilinear HSS, producing t squared digests to send to Bob in total. Bob inputs each column of my into a separate instance of the encryptor side of the bilinear HSS protocol. Because it works in one simultaneous round, the bilinear HSS gives Alice and Bob outputs from all pairs of these instances. If we let Bob's instance define the row and the index of Alice's index define the column, then we find that all these dot products give the entries of the matrix product x times my. And since my is a multiple identity matrix, this just scaled every entry in mx by the same scalar y. Finally, the communication complexity is proportional to the number of entries of my, as they must all be encrypted, plus the number of rows of mx, since every row must be digested. These are both t squared, so the communication complexity must be t squared, or equivalently, n to the 2/3. Next, I'll get into some preliminaries needed to understand how we can build bilinear HSS. Assume that we have a group G that can be split into a product of two groups, F and H. So as the subgroup F is generated by some element little f, it's cyclic, and we need this subgroup to have an easy, efficient algorithm for a discrete log. The other subgroup H must have hard discrete log, and it must be impossible to distinguish an element of H from a random element of H from a random element of the entire group. This technique is useful for additively homomorphic encryption. However, we need something stronger than just additively homomorphic encryption. The stronger tool we need is a distributed discrete logarithm operation, or ddlog. Assume that Alice and Bob have group elements u0 and u1, whose ratio encodes the message z in this easy discrete log subgroup generated by f. If we allowed interaction, ddlog lets them non-interactively find secret shares of z just from these group elements. Now, the crucial part of this is that this is done without any interaction. With interaction, it would be easy to just do a normal discrete log on one party or the other. But without interaction, it turns out there are still protocols that take advantage of the easy discrete log subgroup to let you get these secret shares. OK, so how do we use the ddlog operation to compute bilinear HSS? Assume that we have a correlated common reference string containing the description of the ddlog group and some generators g0 to gn. The hasher computes a Peterson commitment D to their inputs x1 to xn using randomness R and the generators g0 to gn. And they send this commitment as a digest of their inputs. Simultaneously, the encryptor generates a sort of generalized Elgamal ciphertext with multiple, it's like a vector ciphertext rather than one, making use of the multiple generators, but all using the same randomness S. So the encryptor generates a Elgamal ciphertext encrypting their input vector Y, and sends these ciphertexts to the hasher. To get their inputs to the DD log, the hasher does the exact same operations as when finding the digest D, but uses the ciphertext group elements instead of the generators. And the encryptor takes the digest to just the power of their secret value. The ratio U0 over U1 must be in the easy discrete log subgroup to get anything useful out of this. If we substitute in these ciphertexts, we see that there's a f to the power of xi's times yi's. So that's what we want, but it's hidden behind some like powers of g. However, it turns out these exact same powers of g appear in U1 as well, so they cancel out. In the end, we get f to the power of x dot product of y. So the distributed discrete log operation it will give us secret shares of the inner product of x with y. So we can build bilinear HSS, and we've already seen how that implies succinct half-chosen vector OLE. Next is our applications, succinct HSS. We start with an overview of HSS for restricted multiplication straight line or RMS programs. An RMS program looks kind of like an arithmetic circuit, but with some restrictions on what operations are allowed. Values in the program are divided into input wires and memory wires. The main input wires are just the inputs, and there's no way to get any new input wires. But they can be converted into memory wires. And memory wires can be multiplied by input wires or added together. The main restriction is just that you cannot multiply two memory wires together. So what this means is every time you want to do a multiplication, you have to do the multiplication with an input. You cannot multiply two memory values together. So it's easy to evaluate polynomials in RMS programs just by computing each term separately and adding them together. And you can also evaluate branching programs, which gives you NC1. To run these RMS programs inside HSS, the two servers have some secret shares of a secret key SK. The corresponding public key is used to encrypt the inputs with the ciphertext given to both parties. The memory values become subtractive secret sharings of the secret key times the plaintext value. So far so good. This is how you can do HSS. But how do you compute, how do we do succinct HSS? How do we compute the dot product of some RMS program like this with some vector y that we want to input succinctly? Assume that we have some circuit, assume that the circuit is C1, the circuit outputting the first component of C of x, so it should be multiplied by y1. Then we can perform a transformation like so. If we take each of these conversion operations that takes an input wire and turns it into a memory wire, and turn it into a multiplication by y1, that makes every term in this polynomial we're evaluating get multiplied by y1. And so the result gets multiplied by y1. So then we can add together these results to get the dot product. And if we want to input the y's succinctly, all we have to do is put the y's into half-chosen vector OLE. The scalar is the secret key. And then we get secret shares of the product of the secret key with the inputs y. So that means we can load these values as memory shares with only sublinear communication. Finally, I'd like to show how these techniques can be used to build distributed point functions. We want to generate an additive secret sharing of some vector that is all zeros, except for in one position. This position is chosen by all the parties together. It's the XOR secret share of some inputs AI for all I. Also, the value at this position is multiplicatively secret shared across all the parties. In fact, we do something stronger. We can build a PCG that outputs a batch of these things more efficiently, just a single one, but I will not get into that in this talk. So our algorithm works using by the following invariant. At each step j, the first j parties will have a DPF, secret shared among them, based on their j inputs, the alpha 1 to alpha j and beta 1 to beta j. In each step, we want to add an additional party by permuting the DPF according to their alpha and then multiplying by beta. So it turns out that we can represent this using the RMS program operations. So first thing to look is that permuting a vector can be viewed as just multiplying it by some matrix. So it's a linear operation of the vector. Now we need to represent this matrix using our RMS program. It turns out this matrix is built out of just polynomials in alpha. So we combine that together with multiplying by beta. Then we get a program for evaluating this like permutation and multiplication operation to introduce an additional share into the DPF. We get a program for doing this using succinct HSS. Our DPF protocol then works as follows. Party 1 starts by just generating local shares of a truth table based on its own inputs. Then in the next step, parties 1 and 2 run succinct HSS to permute party 1's truth table according to party 2's input. So the truth table, again, is only used linearly, so it can be the hashed input, which takes only communication sublinear in that input. The second party's beta and alpha are input normally. It can be nonlinear in those. And then we use succinct HSS to compute the product. So this gives secret shares of this combined DPF for these two parties. Then now in the I step, from step I-1, we have these secret shares for the I-1 parties. And we want to do this product permutation and multiplication operation for the combination on the truth table. Because it's linear, it's the same as applying it to each share individually and then combining the outputs. So we can do the hashing and inputting scheme same as before. Finally, I'd like to say a little bit about the power ring LWE problem that lets us get square root communication in the lattice setting for succinct half-chosen vol. So it's a LWE problem where the public matrix is chosen as just powers of some random element A. The dual problem, SIS problem, this has been studied before. It's called vanishing SIS. And I'd be interested in like results on one way or the other on its the security of this LWE problem. To summarize, we have shown how to use DCR or class groups to construct bilinear HSS, succinct half-chosen vector OLE, and succinct HSS. The succinct HSS is useful for distributed point functions and sublinear MPC for arbitrary many parties on layered circuits. Thank you.
All right, so thanks for the talk. Any question? No. So I have questions about the power LW assumptions. So is there anything known regarding these new LW assumptions? Like, is there anything known regarding relations with other?
I'm sorry, I cannot hear you over the echo.
My questions about the power LW assumptions.
Sorry, what did you say?
I have questions about the LW assumptions.
Mm-hmm.
Are there known relations with other assumptions?
There's some. I think there's a known relation on the SIS problem, but not the LWE. I think it can be related to some. I can't remember if it was like extremely low noise LWE or NTRU, but some problem along those lines. I think there's a relation.
Okay. Thanks. All right, so let's end the session, and there is the award session in 1 hour and 10 minutes at 7. So anyway, so let's thank the speaker and.
Hello. Can I ask you to leave the downstairs area because we're doing some refurnishing for the ramp session in the back? So you feel free to hang out upstairs, but we need the downstairs area free of people. Thank you.